Greetings, Saints, man. I hope you guys are doing well. Appreciate you, those of you who made the time and have been flexible for me doing this live stream a little bit earlier than usual. Tonight is Meet the Teachers Night as I do this live stream. So just giving you guys a heads up. My apologies for the late notice, but here we go. So within this lesson, this is where we're going to take the perimeter and area of a polygon and a coordinate plane. So the first thing we're actually going to sit here and do is we're going to define what a polygon is. I want us to get away from using the word shape and start to use more academic terms. I think I've told you guys there's some of these things that are a little bit problematic because they're ambiguous. For example, we call something a corner. It's not that we're just trying to uh, litter academic speak and make things unnecessarily complicated, but we do want to be specific. We are creating a logical system. It's rather important for us to make sure that we are utilizing the correct terms so that we don't have flaws within our system. And we have enough words and ideas to express what we're doing here. So first thing we're going to talk about is a polygon, which is a geometric figure that is composed of a minimum of 3 line segments. All right. And each side will intersect with exactly 2 sides. And at each, there is a vertex. Now, again, getting away from this idea of corner, we're going to call these a vertex. All right. So play a little fun little quick game, which is it a polygon or not? I usually have here a shape fixer. Let me see here. I think I have that tool here. Where to go? Draw, insert, draw. There we go. Automatic shapes. Lovely. So here's one. Ha! Good thing I have the software, right, boys? There is a 3-sided figure, right? I have to have the minimum of 3 line segments. Okay. And is this a polygon or not? Well, here's what we would call that vertex, right? This right here. This is why I usually don't always just use this tool right here, guys. I have to turn it on and off. But that is the vertex, all right? I have 3 of them. I have the same number of vertices as I do sides. Does it meet all these requirements? And the answer here is going to be a yes, all right? Let's do another one here. All right? Is this a polygon? Well, here's the issue. It intersects with exactly 2 sides. Here, we have this guy, it intersects with 2 sides. This guy intersects with 2 right here and here. The issue is regarding the vertex because this line segment here at this top portion doesn't intersect with anything. So this is a no. I want us to get away from this idea of open and closed figures. The problematic part is still this. Oops, is still this little portion up top, which seems like it's an overhang. That's not the academic term. I think you guys have a good sense of what makes a polygon or not. But yeah, it doesn't meet at a vertex. This is missing 2 sides for it to intersect with. It only has one that it intersects with down here at the top of that triangle. So here's another one. Oops. Or it made it its own little triangle there. Is this a polygon? And the answer is a resounding, ready for it? Yes, this is a polygon. In fact, it's a quadrilateral, right? I have 1, 2, 3, 4 sides. Okay. 1, 2, 3, 4. This, it's not asking about it fulfills all the definitions. Every single side meets with a minimum, or yeah, side intersects with exactly 2 sides. Each one meets at a vertex, right? Here's the vertices 1, 2, 3, and 4. Same number as that have sides. Okay. So we're good to go there. Problem is that some of you guys aren't used to seeing it this way. Now, this actually is called a chevron, okay? And but it meets the definition. And this is where we're gonna have to talk about another issue called convexity versus concavity, and that's something we're gonna discuss shortly. Last but not least, I have this guy right here. All right. And we're going to kind of straighten that up. And I have 1, 2, 3, right? and it all intersects at vertices, correct? And I have sides, except for my sides have to be what type of thing? Line segments, all right? This curve on the top portion makes this not a line segment. So this does not meet the definition, then since that top portion is not a line segment, so this guy is a no, all right? Next, let's talk about classifying polygons, all right? Let me actually turn off my auto shape tool because it's gonna create some problems for me. So we're gonna first have the number of sides, and we're gonna define all these, and then we're gonna have the name of the polygon. All right, we're gonna go with 3, 4, 5, 6, 7, 8, 9, and then even 10 sides, okay? Oh man. That didn't work out for me. 3, 4, 5, 6. There we go. I got my little table now. There we go. 7, 8, 9, 10. And then I'm going to give you one more, which we're going to call N. Okay. So we have these names of these, like the three-sided polygon. We had one up top, right? The very first one we drew. You guys know, of course, that's the triangle. And then I've got over here the four-sided, which we talked about this in class. We don't just call it a square. The four-sided default is actually called a quadrilateral. That extends the definition to any polygon with four sides, right? A square being a very specific instance of quadrilateral. Then I have the pentagon. And then we have these agons happening now, right? Penta meaning 5, hexagon, 6. I have a heptagon. This one actually cracks me up because people want to say, because it's 7, they want to say septagon. It sounds like a, I don't know, like a transformer made out of a porta potty. It's kind of a strange deal. I don't know. It's kind of weird. Octagon. The 8-sided, right? Like, you know, like the octopus has 8 arms. The nonagon is the 9-sided, and the decagon, right? Like this thinking about the decimal, right? To the decimeter, right? Those things being to a 10th, so to 10. Now, mathematicians decided once upon a moon that there are names for these things. There's a Greek prefix for all of them. And that's fine. Like the 11-sided figure is actually, this is just a little bit of trivia. People like who know this sort of thing is a guy like me, right? How does this help you? Maybe in Jeopardy someday. This is an 11-sided figure. It's called the hendecagon, and nobody really cares. After 10 sides, you can literally just say the number and then agon. An 11-sided figure is called an 11-agon. A 20-sided figure is called a 20-agon. That is acceptable because what we really need to know is how to utilize this as we're learning. And how to use it formulaically. Now, all of these you guys must memorize. The first 8 polygons, right? Triangle through decagon, because you are going to encounter on your assessments from here on out. I'll ask you just a plain question potentially about an octagon, and you have to know that's the one with 8 sides, right? It's gonna be critical to whatever method you're gonna use to solve the problem, all right? Now, what I was just talking about before, right? We have this figure that's up here. This guy's unique amongst these. It's still a polygon, but not like the triangle. It was a quadrilateral. And this is where we have the idea of concave versus convex, all right? A concave, I think the thing that you guys probably even remember maybe from middle school is that this would cave in, all right? And that's nice. But the thing I want us to see is with something being concave versus convex. Like convex is one of these guys, right? This is a quadrilateral that is, oh man, it's a pretty rough one. I told you guys, I work really hard at this to be just okay at it. Versus here's another concave polygon, but it doesn't have the same number of sides. All right. Just like pretend to like here, so I'm going to fudge my way through there because I have my vertices here, right? All these, you guys call them corners, but that's not what it is. It's called a vertex. And the reason we use that is because, like, for example, if we were working in a 3-dimensional solid, in other words, if you had a cube, you wouldn't call the little pointed spot a corner, okay? It actually has a name. The issue here, it has to do with how, when we define these, has to do with what's the diagonal. So a diagonal, mathematically speaking, means that it connects two non-adjacent vertices. All right. An adjacent vertex is going to be a side. Here's, oh goodness, need that. There we go. From here to here, right? That is a side. This vertex is adjacent. It's next to it. When it's non-adjacent, we're going to talk about this more in the next chapter. We wind up skipping one and we go across. So that's my diagonal. When we have concave versus convex, concave polygons, the diagonals are all interior to the polygon, versus when we have it as a convex, gentlemen, this one's convex. This one's concave. My apologies. I'm like doing everything backwards here. Okay. When it is convex, they're all interior. When it's concave, at least one diagonal is exterior. So it's this. I can draw interior diagonals, but boom, I went right here to here and I have an exterior diagonal, therefore making this guy concave, right? We have that idea where it's caving in. You have polygons all around you. I'm looking at a wall in front of me right now, in this doorway. So thinking about a doorway. A polygon, right? All vertices or all sides. It's got a certain number of vertices. I got 1, 2, 3, 4, 5, 6, 7, and 8. 8 sides. This is actually specifically a concave octagon. 8 sides, there's 8 vertices, right? Oops, oh my goodness. Let's go back, get that back. There we go. That's a vertex right there, right? I'm gonna have 8 of those. 2, 3, 4, 5, 6, 7, and 8. Always have the same number of vertices as sides, all right? And there we go. Continuing on, I gotta get cooking here because I'm gonna have parents coming into my classroom shortly. We're gonna talk about the perimeter, which is the length around a figure. In other words, the length or distance. Okay, so we're going to calculate some perimeters and we will never ever graph it. So we're going to find the perimeter of triangle ABC with vertices, which is the plural for vertex, of A, which is, and by the way, when we have geometrically speaking, when we're calling something a triangle, we'll collect 3 points and we're going to draw a little triangle in front of it. I'll reference that in the future when we get to studying triangles, but for right now, it's not that big. A is -1, 4, B is 2, 4, C is 2, -1. All right. And let's do it. Do not graph. Because it's going to be irrelevant. It wouldn't help you if you did. All right, and you're going to see why very quickly. So the idea here is I have a triangle. This isn't really a graph. If I were going to graph it, right, I'd have a coordinate plane, right? This guy. But I'm not going to do that. I'm just going to draw a triangle just to make this a little bit less abstract. And to see that I have 3 sides, I need to calculate side AB, right, this one, BC, and then AC. To do that, I'm going to need to utilize the distance formula, all right? So for AB, now, gentlemen, I referred to this earlier this week when I taught you guys the distance formula. The idea was like, hey guys, it's on Mondays, like you guys you're gonna have to do the distance formula as like a step within these problems. It's not gonna just be like on the quiz that you guys just took. It was the point of a problem is like the entire purpose of a problem. Now it's just a step within it. So I was like, oh yeah, that's gonna happen in the future. Well, the future's now. AB, I'm going to take the difference of -1, right? It's the difference of my x's, -1 and 2. So -1 minus 2 squared plus 4 minus 4 squared, which is going to give me a negative 3 squared plus 0, which is going to give me rad 9, which is 3. Okay? BC. I know I'm moving quickly, but you guys can go back and slow me down or pause the video. 2 minus 2 squared, okay? And we have 4 minus 1 squared, right? Because that's what's going to happen with these guys. The y, the 4 and the 1, it's going to be 4 minus the negative 1, the minus, right, is going to become this plus. And then 2 minus 2, 0 squared, which is 0, plus 4 plus 1, which is 5 squared. Okay, so it's going to be a rad 25. Square root of 25 is 5. All right, so I have 3, I have 5. And I have AC, square root of, and I'm going to wipe this guy down here. Here we go. This is my x sub 1. This is my x sub 2. So I'm going to have a negative 1 minus 2 squared plus y sub 1, y sub 2, 4 minus 1 squared, which is going to give me a negative 3 squared plus 5 squared, which will give me a rad 9 plus 25, which would be a rad 34. And we talked about this in class. This number right here, as we talked about the Pythagoreans, that is an exact number and it's perfect as is. So don't change it. I have no square numbers or no square factors that go into 34. So I have to leave it that way. I don't care that it's 2 times 17. 2's not square. So this guy gets stuck just as is. Don't give me a decimal approximation. I want equals, right? I want what it's equal to, not what it would be about. So we want to be precise here. I need to take the sum of AB plus BC plus AC as my perimeter, which is going to be 3 plus 5 plus rad 34. 3 plus 5, of course, is going to be 8. I cannot combine rad 34, remember? And that's going to be my units. And that's because I just can't, right? It's like when you go to the grocery store, you're collecting like terms. You wouldn't add x plus y. X plus y is equal to x plus y. You wouldn't combine the apples and the oranges into one bin. That'd be crazy, all right? Moving on, got 2 more examples for you guys. We're going to find the area. Triangle ABC with vertices. Where A is going to be 1, 3. B is 3, negative 3. And C is negative 2, negative 3. All right. So, area. I need a formula. Oh, get it. Write this guy right here. My area formula for a triangle is that the area is equal to 1/2 of the base times the height. So in this coordinate plane, if I were to, I'm going to do a quick little graph, that height winds up being a perpendicular height, okay? So I have 1, 3, that's A, 3, negative 3, that's my B, and my C is negative 2, negative 3, all right? So my A to B, or B to C, good. The first thing is I need to figure out is how much is this base. So I'm going to say this is equal to 1/2, and my counting principle says that this length right here, right? If I go left to right, is going to be a 5. Could I do the distance between the two? Yes, right? And of course, you guys can even see the result. When I do negative 3 minus 3, it'll be a 0, right? 3 minus 2 is 5. Square that. It's 25, and the square root would be 5. The key, though, is this one right here. This distance, okay? Now, we don't have the tools yet. We will actually be able to calculate where these intersect at some point and prove that through that right angle, that is going to be my perpendicular height. For right now, I'm going to be using, again, this counting principle, right? AKA this kind of the silliness of that ruler postulate we talked about before. And this guy right here, this height is equal to 6. It's 6 high, okay? 1/2 of 5 times 6, which is going to be 1/2 of 30, which is equal to 15 meters squared. All right. Last problem we have here, we're going to find the area of a of quadrilateral ABCD. If A is -3, 3, B is 3, 3, C is 3, -1, and D is -3, -1. All right. Now, the areas here. The area of a rectangle is the same effectively as, and again, this is a quadrilateral because it has 4 vertices, and you have, remember, as I said before, let's make a little note of it. We're going to have the same number of vertices as sides. Okay. Area of a rectangle is the length times the width. Okay. Which in a square, which is a rectangle, right? It's the length is equal to the width because they're the same. So it's length times length, or width times width, which should just be the side times itself, or the side squared. Okay. Now, what do we have here? Let's go ahead and I'm just going to graph this guy out real quick in a coordinate plane, and we'll be on our way. All right. -3, 2, 3, comma 3, 3, 3, 3, -1, -3, 1. Have my A, my B, my C, and my D. They typically go, gentlemen, when you list them this way, they will go either clockwise, okay, as you list your vertices, or counterclockwise, all right? It doesn't have to be alphabetical. So A to B, B to C, C to D, and then A connects back to D, showing me that I've got the 4, all right? This width right here is equal to 6. This length right here is equal to 4. So my area is equal to my length times my width, which is 6 times 4. So my area is equal to 24 units squared. Okay? And there you go, gentlemen. We got enough to work with, and I'll see you guys in class as we complete these problems tomorrow.